In the quiet hours when the world slows and the mind turns toward rest, there is a particular comfort in hearing how we came to know what we know. Tonight, we will wander together through the story of forensic science, the careful and often surprising journey of how humanity learned to read the silent testimony left behind at the scenes of crimes. This is a tale of patience and observation, of curious minds and accidental discoveries, of the slow accumulation of methods that would eventually allow us to speak for those who could no longer speak for themselves. We will begin in a time before fingerprints were known to hold identity, before blood could reveal its secrets, when the investigation of death was often little more than guesswork dressed in authority. To understand where forensic science began, we must travel far back, to the ancient civilizations that laid the foundations of law and medicine. In ancient Egypt, around 3000 BCE, the coroners of the time were already developing crude methods for determining causes of death. The Edwin Smith papyrus, dating to approximately 1600 BCE, contains some of the earliest known medical writings and describes examinations of wounds in remarkable detail. The Egyptians understood that the body could tell stories, that the nature of an injury might reveal how it was inflicted. They recorded their observations, though their methods were limited by the knowledge of their age. In China, during the Zhou dynasty around 1000 BC, officials were tasked with investigating deaths and injuries, and they developed systematic approaches to examining bodies. The Chinese also recognized the importance of documenting injuries accurately, understanding that written records could serve as evidence in legal proceedings. These early efforts, though primitive by modern standards, represented the first fumbling steps toward a science that would one day transform criminal investigation. The ancient Romans contributed significantly to the development of forensic thought, largely through their sophisticated system of law. Roman legal codes required physicians to examine bodies in cases of suspicious death, and the Emperor Augustus specifically mandated that physicians perform autopsies in certain circumstances. The Roman physician Galen, working in the 2nd century CE, conducted detailed anatomical studies that would influence medical science for centuries. Roman legal proceedings also allowed for the testimony of physicians as expert witnesses, establishing a precedent that would echo through the ages. The Romans understood that specialized knowledge could assist in the administration of justice, that trained observers might perceive things that ordinary people would miss. This recognition of expertise as a tool for truth would become fundamental to the forensic enterprise. The medieval period saw a temporary retreat from the systematic study of death and injury. Religious beliefs often discouraged the dissection of human bodies, and the understanding of disease and injury remained largely within the realm of superstition and classical authorities. Yet even in this period, there were those who persisted in observation and documentation. In 13th century China, the physician Sun Tzu wrote the earliest known treatise on forensic medicine, a work titled Washing Away of Wrong Cases. This remarkable document described in detail how to examine wounds, how to distinguish injuries inflicted before death from those inflicted after death, and how to determine whether death was due to suicide, accident, or homicide. Sun Tzu emphasized the importance of careful observation and logical reasoning, principles that would later become central to forensic science. His work was far ahead of its time, but it would be many centuries before similar systematic approaches emerged in Europe. The Renaissance brought a renewed interest in the human body and its mysteries. Andreas Vesalius, the great Flemish anatomist, published his groundbreaking work on human anatomy in 1543, pioneering techniques of dissection that would eventually benefit forensic science. The study of anatomy advanced rapidly, and physicians began to understand the body with unprecedented precision. This knowledge would prove essential when physicians began to apply their understanding to questions of legal importance. The Renaissance also saw the development of more sophisticated legal systems in Europe, systems that increasingly demanded evidence and reasoning rather than trial by combat or other primitive methods of determining guilt. The stage was being set for the birth of forensic science as a distinct discipline. The 18th century brought significant advances in the understanding of death and its causes. The Italian physician Giovanni Battista Morgagni published his monumental work on pathological anatomy in 1761, describing in meticulous detail the changes that various diseases produced in the organs of the body. Morgagni's work demonstrated that death was not a single event but a process, and that the causes of death could be identified through careful examination of the body after death. His approach of correlating clinical symptoms with anatomical findings established a methodology that would prove essential for forensic pathology. Meanwhile, in France, the physician Antoine Louis developed a system for identifying wounds and determining their causes, and his work would influence the development of forensic medicine throughout Europe. The formal recognition of forensic pathology as a medical specialty began in the late 18th and early 19th centuries. In 1795, the French government established the first chair of forensic medicine at the University of Paris, formalizing the teaching of methods for examining bodies in legal contexts. This institutional recognition marked a turning point, establishing that the investigation of death was not merely a legal matter but a field requiring specialized medical knowledge. Similar positions were established in other European countries, and the discipline of forensic medicine began to take shape as a coherent body of knowledge and methods. The doctors who filled these positions developed increasingly sophisticated techniques for determining causes of death, for estimating time since death, and for identifying injuries and their mechanisms. They learned to read the body as a text, to interpret its signs with scientific rigor. The early 19th century saw the development of one of the most enduring forensic techniques, though its significance would not be fully recognized for many decades. In 1805, the British colonial administrator William Herschel, working in India, began using hand and foot impressions as a means of identifying criminals. Herschel was not interested in the unique patterns of fingerprints. He simply wanted a reliable way to prevent convicted criminals from claiming to be someone else upon their release. He had prisoners imprint their hands and feet on contracts and other documents, creating a permanent record of their identity. Over the years, Herschel accumulated thousands of these prints, and he began to notice that the patterns never changed and appeared to be unique to each individual. Yet he never pursued the implications of this discovery for general identification purposes. His work remained a curiosity, an administrative convenience rather than a scientific breakthrough. The world would have to wait for others to recognize the true significance of the whorls and ridges that covered human fingertips. The first systematic study of fingerprints as a means of identification is credited to the British scientist Francis Galton, who began his research in the 1880s. Galton, a cousin of Charles Darwin, was fascinated by the variation in human features and sought to determine whether fingerprints might provide a reliable means of distinguishing individuals. His work built upon earlier observations by physicians such as Ernst Kucklick in Germany and H. Faes in Argentina, but Galton was the first to develop a comprehensive classification system and to demonstrate mathematically the uniqueness and permanence of fingerprint patterns. He published his findings in 1892 in a work titled Fingerprints, establishing the scientific foundation for what would become one of the most important tools in forensic science. Galton calculated that the chance of two individuals sharing identical fingerprints was about 1 in 64 billion, a number so large as to make identification virtually certain. His work transformed fingerprinting from an administrative trick into a rigorous scientific method. The practical application of fingerprint identification was developed primarily in Argentina and England. In Argentina, the police inspector Juan Vucedic developed an alternative classification system and began using fingerprints to identify criminals in the early 1890s. His system was adopted by the Argentine police in 1896, making Argentina the first country to use fingerprints for routine criminal identification. In England, the Metropolitan Police adopted fingerprinting in 1901, following the recommendation of a committee that had studied Galton's work. The system spread rapidly throughout the world, and by the early 20th century, fingerprint identification had become a cornerstone of criminal investigation. The simplicity and reliability of the method were revolutionary. An impression left at a crime scene could be compared directly to the prints of a suspect, providing evidence that was essentially incontrovertible. Fingerprinting represented the first forensic technique that could definitively link an individual to a specific location at a specific time. While fingerprinting was transforming criminal identification, another French scientist was developing an entirely different approach to the identification of criminals. Alphonse Bertillon, a French police officer and anthropologist, had become frustrated with the limitations of existing methods. For identifying repeat offenders, in the 1880s, he developed a system of body measurements that he believed could reliably distinguish between individuals. Bertillonage, as his system came to be called, involved measuring 11 specific dimensions of the body, including the length of the head, the span of the arms, and the length of the feet. The theory was that these measurements, taken together, would be unique to each individual and would not change significantly over time. Bertillon's system was adopted by the French police in 1882 and was used successfully for several decades. It was eventually superseded by fingerprinting, which proved more reliable and easier to use, but Bertillonage represented an important early attempt to apply scientific principles to the problem of criminal identification. The late 19th and early 20th centuries saw numerous other advances in forensic science. The study of blood became increasingly sophisticated as scientists learned to distinguish between human and animal blood and to identify blood types. The Austrian immunologist Karl Landsteiner discovered the ABO blood group system in 1900, a discovery that would eventually prove crucial for forensic blood analysis. Initially, blood typing could only exclude suspects rather than identify them, since many individuals shared the same blood type. But even this limited information could be valuable in investigations, and the technique was quickly adopted by forensic laboratories around the world. Blood typing represented the first time that serological evidence could be used to narrow the pool of possible suspects in a criminal investigation. The analysis of bloodstains at crime scenes also developed during this period. In 1895, the German scientist Paul Kirk wrote an article describing how the shape and distribution of bloodstains might reveal information about the events that produced them. His work was largely ignored at the time, but it represented the first steps toward what would later become the sophisticated discipline of bloodstain pattern analysis. The study of how blood behaves when it strikes surfaces, how the angle of impact affects the shape of the stain, and how the pattern of stains can reveal the movements of individuals during a violent encounter would eventually become an important forensic specialty. But this development would have to wait for later researchers who would build upon Kirk's initial insights. The field of toxicology also advanced significantly in the late 19th century. The detection of poisons in the bodies of the dead had always presented a particular challenge for forensic scientists, as many poisons leave no obvious signs of their presence. The development of chemical tests for common poisons such as arsenic, strychnine, and cyanide allowed toxicologists to identify these substances even when no obvious symptoms were present. Perhaps the most famous early case involving toxicology was the murder of the French physician Jean-Pierre Maupin-Groinard in 1851, whose body was exhumed and found to contain a lethal dose of arsenic. This case demonstrated the power of toxicological analysis to reveal crimes that might otherwise have gone undetected. The science of detecting poisons continued to advance throughout the 19th and 20th centuries, eventually becoming capable of identifying even trace amounts of a wide variety of substances. Ballistics, the study of projectiles and their behavior, also emerged as a forensic discipline during this period. The development of firearms had created new possibilities for violent crime, and investigators needed methods for determining whether a particular bullet had been fired from a particular weapon. In the early 1900s, scientists began to study the markings that firearms leave on bullets and cartridge cases. Each firearm produces unique markings as the bullet passes through the barrel, and these markings can be used to determine whether a particular bullet was fired from a particular weapon. The comparison of bullets under a microscope became a standard forensic technique, and the development of increasingly sophisticated microscopes and mounting techniques improved the reliability of these comparisons. Ballistics would eventually become one of the most important forensic specialties, particularly in cases involving firearms. The first half of the 20th century saw the refinement and systematization of many forensic techniques. Police laboratories began to be established in major cities around the world, providing specialized equipment and expertise for criminal investigations. The FBI laboratory, founded in 1932, became one of the most prominent forensic facilities in the world and served as a model for other laboratories. Scientists working in these laboratories developed increasingly sophisticated methods for analyzing evidence of all types, from fibers and hairs to paint chips and soil samples. The principle that every contact leaves a trace, formulated by the French criminologist Edmond Locard, became a foundational concept in forensic science. This principle held that every criminal brings something into the crime scene and takes something away, and that these trace materials can be used to establish links between criminals and scenes. The analysis of hair and fibers became an important forensic discipline during this period. Hair is remarkably resilient and can survive for long periods of time, and its characteristics can provide useful investigative leads. The microscopic examination of hair can reveal whether it came from a human or an animal, and in some cases can provide information about the race and possibly the hair color of the individual from whom it came. Similarly, the analysis of textile fibers can establish connections between individuals and crime scenes or between victims and suspects. These techniques, while less definitive than fingerprinting or DNA analysis, could provide valuable corroborating evidence and help investigators narrow their focus. The study of document examination also developed significantly during this period. Handwriting analysis had been used for centuries as a means of establishing identity, but the scientific study of handwriting as a forensic tool began in the 19th century. Document examiners developed techniques for comparing handwriting samples and for identifying characteristics that might indicate forgery or disguise. The analysis of ink and paper also became important, as scientists learned to distinguish between different formulations and to date documents based on their physical and chemical properties. These techniques proved valuable in cases involving questioned documents, from contracts and wills to threatening letters and suicide notes. The discovery of deoxyribonucleic acid, or DNA, in 1953 by James Watson and Francis Crick opened an entirely new chapter in the history of forensic science. DNA is the molecule that carries the genetic instructions for the development and functioning of all living organisms, and its structure contains a code that is unique to each individual, with the exception of identical twins. The realization that this genetic code could be used for identification purposes represented a revolution in forensic science. DNA analysis could identify individuals with virtually absolute certainty, could link crime scene evidence to specific suspects, and could exonerate individuals who had been wrongly convicted. The first criminal case in which DNA evidence was used was the murder case of Colin Pitchfork in England in 1986. The police had recovered from the victim but had no suspect, and the forensic laboratory used DNA profiling to compare the crime scene DNA with samples from thousands of men in the area. The technique worked, and Pitchfork was convicted largely on the basis of the DNA evidence. This case demonstrated the power of DNA analysis and sparked its rapid adoption by forensic laboratories worldwide. The early DNA profiling techniques required relatively large samples of biological material, and the process was time-consuming and expensive. Samples had to be sent to specialized laboratories, and the analysis could take weeks or months. But as the technology improved, it became possible to analyze increasingly smaller samples and to obtain results more quickly. The development of the polymerase chain reaction, or PCR, in the 1980s revolutionized forensic DNA analysis by allowing scientists to amplify tiny amounts of DNA into quantities sufficient for analysis. PCR made it possible to analyze DNA from samples that would previously have been too small to test, including stains, hair shafts, and touched objects. This technique dramatically expanded the types of cases that could be solved using DNA evidence. The establishment of DNA databases represented another major advance in forensic science. These databases store DNA profiles from convicted offenders, crime scene evidence, and missing persons, allowing investigators to search for matches between evidence and known individuals. The United Kingdom established the first national DNA database in 1995, and similar databases were subsequently created in countries around the world. The FBI's Combined DNA Index System, or CODIS, became operational in 1998 and now contains millions of DNA profiles. These databases have proven invaluable for solving crimes, particularly serial crimes where the same offender may have left DNA at multiple crime scenes. The power of DNA databases was demonstrated dramatically in the case of the Golden State Killer in California, who was identified in 2018 through a technique known as genetic genealogy, which involves searching public genealogy databases for relatives of a known DNA evidence. The development of touch DNA analysis represented another significant advance. This technique allows forensic scientists to analyze the DNA left behind by the skin cells and oils transferred from a person's fingertips when they touch an object. Touch DNA analysis proved revolutionary because it could potentially link any person who touched an object to that object, regardless of whether they left any other trace evidence. However, the technique also presented significant challenges. Touch DNA samples are often degraded or contaminated, and the interpretation of results can be complex. The question of how much weight to give touch DNA evidence in court has been the subject of considerable debate, and courts have sometimes excluded such evidence when the chain of custody or the reliability of the analysis was questioned. The analysis of bloodstains advanced significantly in the latter half of the 20th century. Researchers such as Herbert Leon MacDonald developed systematic approaches to bloodstain pattern analysis that allowed investigators to reconstruct events at crime scenes. By measuring the angles at which blood droplets struck surfaces, analysts could determine the direction from which the blood had originated. The size and shape of stains could reveal information about the mechanism of impact, and the distribution of stains throughout a scene could indicate the movements of individuals during an assault. Bloodstain pattern analysis became an important forensic specialty, though it has also been the subject of controversy, as some of its claims have been questioned by scientists and courts. Forensic toxicology continued to advance, becoming increasingly sophisticated in its ability to detect and quantify drugs, poisons, and other substances in biological samples. The development of techniques such as gas chromatography and mass spectrometry allowed toxicologists to identify even trace amounts of a wide variety of substances. These advances proved particularly important in cases involving drug-facilitated crimes, where perpetrators might use drugs to incapacitate their victims. The ability to detect these substances in blood or urine samples, even hours or days after they were consumed, provided crucial evidence for prosecutors. Forensic toxicology also became important in cases involving death investigations, where substances such as carbon monoxide, cyanide, or drug overdoses might be responsible for fatalities. The field of digital forensics emerged in the late 20th century as computers and digital devices became ubiquitous. Criminals increasingly used digital technology to commit crimes, and investigators needed new methods for recovering and analyzing digital evidence. Digital forensics encompasses the recovery and analysis of data from computers, smartphones, tablets, and other electronic devices. This field has proven crucial in cases ranging from fraud and identity theft to child exploitation and terrorism. The challenges of digital forensics are considerable, as data can be encrypted, deleted, or hidden, and the volume of data involved in modern investigations can be overwhelming. Nevertheless, digital forensic techniques have become essential tools for law enforcement, and the field continues to evolve rapidly as technology advances. The analysis of forensic evidence has always been subject to questions about reliability and validity. In recent decades, these questions have received increased attention, as scientists and legal scholars have examined the foundations of various forensic disciplines. Some techniques, such as fingerprint analysis and DNA analysis, have been validated through extensive scientific research and have been generally accepted by courts. Other techniques, such as bite mark analysis and some aspects of bloodstain pattern analysis, have faced more scrutiny, and their reliability has been questioned. The National Academy of Sciences issued an influential report in 2009 that called for greater validation of forensic methods and for the establishment of scientifically rigorous standards for forensic laboratories. This report sparked ongoing efforts to improve the scientific foundation of forensic science and to ensure that forensic evidence presented in court is reliable and accurate. The use of forensic genealogy represents one of the most recent and controversial advances in forensic science. This technique involves uploading crime scene DNA profiles to public genealogy databases and searching for relatives who might share genetic markers with the unknown offender. When a relative is found, investigators can use traditional genealogical methods to build family trees and eventually identify the most likely suspect. This technique proved instrumental in identifying the Golden State Killer and has since been used in dozens of other cases. However, forensic genealogy has also raised significant privacy concerns as it involves searching genetic data provided by individuals who may not have consented to such use. Several states have enacted laws restricting the use of forensic genealogy, and the legal landscape continues to evolve as courts and legislatures grapple with these issues. The future of forensic science promises continued advances as new technologies emerge and existing techniques are refined. Rapid DNA analysis, which can produce DNA profiles in under 2 hours, is being adopted more widely and may eventually allow for DNA testing to be performed at crime scenes. Next-generation sequencing technologies offer the potential for more detailed genetic analysis, including the ability to predict physical characteristics from DNA and to analyze complex DNA mixtures more accurately. Forensic scientists are also exploring the use of artificial intelligence and machine learning to improve evidence analysis and interpretation. These advances will bring new capabilities but also new challenges as society grapples with questions about privacy, civil liberties, and the appropriate use of powerful new tools. As we reflect on the long history of forensic science, we can see a clear trajectory from the crude observations of ancient physicians to the sophisticated molecular analyses of modern laboratories. Each generation of forensic scientists built upon the work of those who came before, adding new techniques and new understanding to the accumulated body of knowledge. The progress has not always been smooth. There have been false starts and blind alleys, controversies and critiques. But overall, the story is one of gradual but steady improvement in our ability to determine what happened in the past, to speak for those who can no longer speak, and to bring some measure of justice to those who have been wronged. Forensic science reminds us that the pursuit of truth is a human endeavor, requiring patience, curiosity, and the willingness to follow evidence wherever it may lead. The men and women who have contributed to the development of forensic science have been driven by various motivations: scientific curiosity, professional ambition, the desire to serve justice, or simply the need to solve puzzles. Some, like Francis Galton, were brilliant scientists whose work had applications they never anticipated. Others, like Alphonse Bertillon, were practical reformers who saw problems and sought solutions. Still others were crime scene investigators who developed techniques through trial and error, learning from each case what worked and what did not. Their collective efforts have transformed our understanding of what evidence can tell us and have given law enforcement capabilities that would have seemed like science fiction to earlier generations. Yet forensic science is not merely a collection of techniques. It is also a way of thinking about evidence and truth. The forensic mindset involves careful observation, logical reasoning, and a willingness to follow the evidence even when it leads to unexpected conclusions. It requires patience and attention to detail, the ability to notice small things that others might overlook. It demands humility in the face of uncertainty, an acknowledgement that our methods are never perfect and that our conclusions are always subject to revision. These are qualities that extend far beyond the forensic laboratory, qualities that are valuable in many human endeavors. The forensic perspective reminds us that the world is full of information waiting to be discovered, if only we know how to look. As we consider the future, we can expect that forensic science will continue to evolve in response to changing technology and changing social needs. New types of evidence will emerge as new technologies develop, and old techniques will be refined or replaced as scientific understanding improves. The challenges of validating new methods and ensuring their reliability will continue to be important, as will the need to balance the pursuit of justice with respect for individual rights and privacy. Forensic scientists will need to adapt to these challenges, maintaining the rigor and objectivity that have always been essential to their work while remaining open to new ideas and new approaches. The story of forensic science is far from over. Indeed, we are probably living in one of its most dynamic periods, as new capabilities open possibilities that previous generations could hardly have imagined. In the quiet moments before sleep, it can be soothing to reflect on how far we have come. The ability to identify individuals through their fingerprints, to reconstruct events from the patterns of bloodstains, to read the genetic code that makes each of us unique, these are remarkable capabilities that have emerged from centuries of patient investigation and discovery. They are tools that have helped to solve countless crimes, to bring closure to victims and their families, and to ensure that those who commit wrongs are held accountable. At the same time, we must recognize that these tools are not infallible, that they must be used carefully and responsibly, and that they raise profound questions about privacy, justice, and the proper limits of state power. As with all powerful tools, their value depends on the wisdom of those who wield them. The story of forensic science is ultimately a story about human beings and our desire to understand the world around us. It is about our curiosity, our persistence, and our capacity for learning from experience. It is about our recognition that the past leaves traces, that events leave evidence, and that careful analysis can reveal what has happened even when no one was watching. This is a deeply human enterprise grounded in our fundamental need to make sense of our world and to resolve the mysteries that surround us. As you drift towards sleep tonight, perhaps you will find some comfort in knowing that there are those who spend their lives devoted to uncovering the truth, to reading the silent testimony left behind, and to ensuring that justice, however imperfect, continues to be pursued. The work continues quietly and carefully in laboratories and crime scenes around the world, a testament to our enduring commitment to knowledge and to the principle that truth